Okay, YouTube, this is my first video on how to graph a rational function, which I'm going to take you through several steps in order to make this graph. And then we'll talk about how we can kind of simplify these steps, just thinking about this out loud. But we say the first thing we always want to do is simplify the rational expression if possible. What I essentially mean is we need to factor any expressions on the top or the bottom. And I notice here that the bottom is a difference of two squares. The top, however, is just 2 times x times x. So there's really not much we can do with that. But this would be our simplified expression to a certain extent. So we're going to say find and plot the y-intercept, if any, by evaluating for f of 0. So essentially, some easy points we want to get out of the way are the zeros, or the intercepts, at least, the y-intercept and the x-intercept. So to find a y-intercept, we just say, well, what we'll do is we'll plug in 0 for x and we'll find y. And in this case, we get 2 times 0 squared over 0 squared minus 1. In other words, we get 0 over negative 1, which is 0. So we already know that this graph is going to pass through the origin. And as a matter of fact, one thing I want to mention about this is anything that had an x in this expression, like this here and this here, when you find the y-intercept, they drop out. So you could always say that the y-intercept is going to be the ratio of your constant terms, top and bottom, for this graph, okay? So now we found the y-intercept, let's find the x-intercept. So when you find an x-intercept, recall that what we're really doing is we're setting y equal to 0. So we have this rational expression here, this 2x squared over x plus 1, x minus 1. And the thing I want to point out is this. If we set the y value equal to 0, what's the only part of this fraction that would cause it to equal 0? It would have to be the top of this, okay? There's no way that we would say the whole thing equaled 0 because the bottom equals 0. It's only when the top equals 0. So to find the zeros, if any, we say, okay, well, let's do this. We set the numerator expression equal to 0 and solve it. So when we do this, in this case I would get 2x squared equals 0. So it would follow that x squared equals 0, and I would get this. I get x equals 0 and 0. I get 0 twice, so it has a multiplicity of 2. So I would say that in terms of zeros, we have one here at x equals 0, and because it has a multiplicity of 2, it's actually not going to cross at that point, just like a normal polynomial wouldn't. So now, the next step is going to be this. Let's find, after we've found the intercepts, let's find and sketch the vertical asymptotes and the horizontal asymptotes. And we usually start with the vertical asymptotes. So recall that vertical asymptotes occur where this is all undefined. And undefined is true if the bottom is equal to 0. So if we were to now set the bottom equal to 0 and solve this, well, we've already factored this polynomial. We can see we get 2 zeros here. And we're going to get x equals plus or minus 1 being our vertical asymptotes. So instantly what I'm going to do is I'm going to go draw those in. So we said find and sketch your vertical asymptotes. And so we have vertical asymptotes at positive and at negative 1. And it is appropriate, certainly, to label these asymptotes. We say x equals 1 and x equals negative 1. I like to label them out of the way. So next up is our horizontal asymptote. So horizontal asymptote, what we're doing is we're looking at the degree of the top compared to the degree of the bottom. And what I notice in this degree situation is that the degrees are balanced. So remember that if the degrees are balanced, what we get is this y equals line where it's the ratio of the leading coefficients, where our leading coefficient on the top and our leading coefficient on the bottom are 2 and 1 respectively. So we're going to get a horizontal asymptote that occurs here at y equals 2. Okay, and this will be that line that our graph tends to get closer and closer to out on the left and right side of the graph. So keep in mind this. We found our y-intercept and our x-intercepts. Now we've found our vertical and horizontal asymptotes. The next step is going to be this. Plot at least 2 points per branch. And that's what we call the parts of this graph here. We call them branches. But essentially what I'm going to tell you is that you need to table some values. And so I hope you're listening here, but in terms of what values should you table, we should always choose 2 values to the left of and to the right of each vertical asymptote. So because I had vertical asymptotes at negative and positive 1, I'm going to choose negative 3 to plug in and negative 2 to plug in. I don't need to plug in negative 1 because it's undefined. I don't need to plug in 0 because that happened to be on our graph already. So I think the next 2 I'll plug in are 2 and 3. And so I just want to indicate that when you do this, you're always going to end up with a ratio of values in the first place because this is a rational function. So let's say, for instance, here we plug in f of negative 3. I would get this. I would get 2 times negative 3 squared. And this is all over negative 3 plus 1, negative 3 minus 1. You'll notice that I plugged it into the factored expression. So I would get on top 2 times a positive 9, which is an 18. On the bottom, I'm going to get a negative 2 times a negative 4, which is a positive 8. So in this case, I get 18 eighths, which is the same thing as 9/4. And I don't think I could simplify that any further. So to get a decimal or a mixed number is not an inappropriate thing. This is going to be 2 1/4. And so let's try this out. What if I were to say plug in -2 now? So if we plug in -2, we get 2 times -2 squared on top. And on bottom we get -2 plus 1, -2 minus 1. So in this case we're going to get 2 times 4 on top, which is an 8. On the bottom we're going to get a +1 times a -3. So we get -8/3 in this particular instance here. Actually, this is a -1 here. I was going to say we get a +8/3 here. So we'll go fill this in. We say at -2 we get a +8/3. So in this case that would be the same thing as 2 2/3 is where it will be. Now plugging in a +2, this is probably the longest part of these problems here, is plugging in values. F of 2, we would have 2 times 2 squared. So I want you to see on the top we're still going to get an 8 just like when we plugged in a -2. But on bottom we get 2 plus 1, 2 minus 1. Here we would get a +3 times a +1, we get a 3. So I notice that I'm going to get some symmetry on this graph here. And just because I know that this will happen the same way with our +3, I know I'll get the same thing as 9/4. That's not always true, but in this particular instance, because of how our functions are set up, it is certainly true. So 2 2/3, and this will be 2 1/4. So now all we're going to do is go graph these points in. And I would say that, well, in this particular instance, -3, we'll go left 3, 1, 2, 3. And we'll go up 1, 2, and a 4th. So it's really, really close to this horizontal asymptote. This left 2 up 2 2/3 would be left 2 up 2 2/3 would be just a little bit higher than that point right there. Before we do anything else, what I want to do is comment on the fact that when we fill these in, we have something that out on the left side has to be getting really, really close to this horizontal asymptote. And as we go through these points, we can see how it starts to increase. And because of the definition of vertical asymptote, we can see how this is going to increase without bound as we get closer and closer to it. So graphing in these other 2 points, we'd say 2, 2 2/3, which would be on this side, and 3, 2 1/4 would be here. We could see how this is going to be sort of symmetrical with that left side of this graph. It looks like this right here. Okay. So now, in order to get the middle part of this graph, it's trapped in here somewhere, and it could do any number of things. It could come down and through here. It could come down, up and through there. It could come down and then go back up. It could come up and then go back down. It is entirely appropriate to pick an x value to plug in here. And in this case, I suppose we could plug in a half. What would our height be at a half? But what I want to see here is this. If we plug in a half, we get 2 times a half squared. And this is over 1/2 plus 1, 1/2 minus 1. What we get here is this. On top, we get a 4th times 2, which is itself a half there. And in the bottom, we get 1.5 times a -1.5, which is a negative, let's see, that'd be a 2.25. So 0.5 over -2.25. Essentially what I want you to see though is that you get a negative result. Because we had a multiplicity of 2 at that 0 for the top right here, we know that it's not going to cross at the 0. So if it's negative right here at a half, negative something, then we know that what our graph's really doing then is coming up from the bottom half, touching and not crossing, and then coming back down. And this would be this part of the graph. So the last thing, we're always responsible for reporting our domain and range. And basically what I can tell you is the domain of this graph is going to be all real numbers except for these x values that we didn't cross. So we would say -infinity up to -1, and then -1 to 1, and then the interval from 1 out to infinity. These would be the domain values of our graph. And I also notice here that on this graph, we never hit any y values. Starting just above y equals 2 is where we started at. So from 2 and including 2 down to but not including 0, those are not in the range. So I would say the range of this is -infinity up to and including 0. We can see that it actually gets to a height of 0, but then it starts up again just over 2 since it never gets to a height of 2 there and then goes to infinity. Cheers.